algorithm's the one we're doing, and there's sort of a nice story from Wikipedia, which you can read about the history about why he wanted to call it dynamic programming. I thought I'd put that up there to do it. But they're actually doing multi-stage decision problems. They were sort of doing something slightly more complicated than we were doing. They were doing indefinite horizon problems. They're doing it going on forever. But now you know what that means. So now you know that we were doing finite stage ones now, and there were ones that go on forever. So this was the classic dynamic programming algorithms that we're talking about. All right. All right. So, whoops, let's do this. Assignment 4 is due in 2 days' time. Please read Piazza, go talk to the TAs. It's not meant to be difficult, but it's not meant to be something you can sort of just do the night before. It's meant to be something you try and you struggle and you say, aha, now I understand. Are there any questions about anything? Okay. So far we've been looking at this representation of a decision network, which is a directed acyclic graph with decision nodes, random nodes, and utility nodes. There's a range for the decision and random nodes, has a unique utility node. And what's important is the arcs into the decision node represent the information that will be available when the decision is made. For each random variable, there's a factor representing the conditional probability for the random variable given its parents. There's a factor for the utility node, and there are no factors associated with decision nodes. Okay, are there any questions about that at all? And then we did variable elimination for creating an optimal policy. And so here, the algorithm is you're going to construct a factor for each conditional. So this is where we ended up last time. We created a factor for each conditional probability table and a factor for the utility. And we summed out the random variables as not parents of a decision node. We selected the decision variable D that's only in a factor with some of its parents. We eliminated D by maximizing, so we summed out the random variables. We eliminate the decision variables by maximizing. It returns both an optimum decision function and a new factor. And we keep just repeating this until there are no more decision nodes. Then we sum out the remaining random variables. Okay, are there any questions about that? That's what we did last half of last time. And as you can guess, I'm going to give some clicker questions. And so we want to make sure there are any questions asked beforehand any puzzlements before we ask them. Does anyone have any questions? Of course, the aim of the clicker questions isn't to actually examine you, but rather to find out what you understand or not. Okay. So here's a decision network. It's the same one we saw last time. It's about buying a car and working out whether it's a lemon or not. The question is, which random variable or variables is or are eliminated, summed out initially before the first maximization? Remember, in this algorithm, we sum out, we created a factor, now we're summing out, and we haven't got to the decision. We want to know which variables we're going to sum out. Okay, how are we going? Does anyone need more time? Anyone need more time? Okay, 3, 2, 1, we'll stop. Yes, the answer is C. We're not going to sum out result, because result is a parent of a decision node. Right, we're not going to sum out result. A and B are wrong. We're not going to sum out results. We're only going to sum out variables that are not parents of a decision node. Okay, so we only sum out lemon. Any questions about that? And the reason we're going to sum out lemon is because we can't use it when we're optimizing by. We don't know whether it's a lemon or not. Right, so when we're going to maximize by, we're not going to know that. Any questions about that? Now the story is we're going to sum out lemons. So now we've got to multiply some factors. Which factors get multiplied? How are we going? Does anyone need more time? Okay, does anyone need more time now? Okay, 3, 2, 1, we'll stop. Oh, that's exciting. We've got to multiply all the factors that contain lemon. Which factors contain lemon? Well, what factors are there? What factors exist? For every random variable there's a factor. There's the probability of lemon, the probability of result given lemon and test, and there's a utility function on lemon and buy. Right, so we did this last time. This is what we got. What do we do when we have lemon? We eliminate lemon. We find all the factors that contain lemon. We multiply them. Right, which factors contain lemon? Well, all of these three do. So we multiply these three together and we sum out lemon. So the answer here is C. They don't even look the same. Okay. Any questions about that? All right, this is all of them where they contain lemon. We now know what good questions for exams there are, don't we? All right. Other questions? We're just going to go through the algorithm. After eliminating lemon, a factor on which variable or variables is created. So what is the factor? What's the factor on that we create? So we're a little bit way through this algorithm here. Actually, we're just at the first line of the repeat. We're summing out a random variable, creating a factor. I want to know which factor is created. A factor on which variables is created. How are we going? Does anyone need more time? Does anyone still need more time? Okay, 3, 2, 1, we'll stop. Oh. That's exciting. Oh, look, it's this. So what we're getting rid of lemon, so we end up with some factor on result. This depends on result. It depends on test. And it depends on buy. So this is some factor on result. If you change the result, you change this. If you change the test, you change this. And if you change the buy decision. We haven't even got to decision networks yet. We're only doing variable elimination. Right? You should know this. It's what we did before for belief networks. So the answer is, where am I? Result, test, buy. Which one's that? C. Oh my goodness. At least the mode. Okay, this is just what we've been doing before for variable elimination. All right, so if you change, think about this way. If you have this product, if you change the value of test, you're going to change the answer for this. So test is a value for this. Now, if you change by, then you change this, so you've got to change the product. If you change, right, we're summing over all the values of lemons, so we're going to look at both values for lemons, but it depends on all of these things, result, test, and by. Any questions about that? All right. We now got to which decision variable is eliminated first. So now at the second one, we've summed out the random variables, and we've got this factor. I want to know which decision variable we can eliminate next. Okay, how are we going? Does anyone need more time? We've got about the right. 3, 2, 1, we'll stop. What? That's the wrong answer. You guys. We're selecting a decision variable that's in a factor with some of its parents. That's only in a factor with some of its parents. By doesn't have any parents. No, sorry. Test doesn't have any parents. So it says here, in a decision variable, it's only in a factor with some of its parents. Right, this one here is only in a factor with some of its parents. The only thing that's in the factor is some of its parents. The answer here is by. By, this thing here is a subset of the parents of by. This is a subset of the parents of by. But test is in a factor with other things that aren't parents, right? Test is in a factor with non-parents. We can't maximize it. It's only in a factor with some of its parents. Right, so this is in a factor with some non-parents. This is only a factor with parents. Right, so this one here, so the answer here is by. We have to maximize by now. We can't maximize test because we don't know what the result is going to be. Right, we can't say if the result's going to be good, we're going to do this test. If the result's going to be bad, we're going to do this test. We can maximize by because we know what the results in the test are. Yes?
So this is kind of the opposite of random variables, because with random variables, there's a mention of if they're parents of things, but not children. Sum out the parents first for random variables.
No, you can variable elimination, you can sum out children or parents. You can do either. Here we can only maximize this if it's in a factor with... Yes, they're more limited. You can't eliminate them arbitrarily. We have to effectively eliminate them backwards. We're going to eliminate the last decision first and the first decision first. And this one here selects the last one. And the last one is in a factor with just its parents. In fact, the whole reason that we did this funny definition of no forgetting is to guarantee that we could actually do it. Right? So we want to here. So we end up with this factor on result, test, and by. And at this stage, we can maximize by because we have its parents in a factor. Okay, any questions? Yes?
How come those
Yeah, we're going to go backwards. We're going to do the very last decision first. We can't maximize test at the moment because we don't know, but we can maximize by. So we're going to go backwards. It's like regression planning. It's a dynamic programming. It's going backwards through time. We're looking at the last one first. What maximizing does? Yeah, so if we have, let's do this. Let's do this. So when we had this one, let's solve this. Let's optimize decisions. So in here we had these three factors. And which variable, there's only one decision node. So what can we sum out? So we have to sum out any variable. Let's move this across to here. Let's move this across to here. Can I do this? Right, so here I want to sum out, which one should I sum out? What should I sum? I want a satisfaction, I want to maximize my utility. Which one here should I sum out or not? Or none? No, forecast is a parent of a decision node. I can only sum out ones that are not parents of a decision node. What should I sum out? Weather. So I should sum out weather. So I'm going to start with the factors. So start with the factors here. Weather umbrella, weather, and weather forecast. So it's forecast given weather, the probability of weather, and the satisfaction given uncertainty in weather. So if we look at any of these, so this is just the weather and umbrella is just my utility function. So now I'm going to sum out this variable, sum out weather, and I construct a forecast like this. Now the question was give an example of maximizing. So what we're going to do here is for each forecast, we're going to maximize the umbrella, the value given umbrella. So we're going to look at the forecast for sunny, and we're going to say, is it better to take it or is it better to leave it at home? If we take it, we get 12.95, and if we leave it at home, we get 49. So we choose the maximum of those two. Right? When the forecast is cloudy, we take it. We can either take it or leave it at home. Leave it at home gives us 14, and leave it at home gives 14, and takes it gives us 5, and choose the maximum value, which is 14. And if it's rainy, there you have a choice between 14 and 7. We're going to choose the maximum. These numbers are sort of a funny mix between probabilities and utilities, because this is sort of the probability times the utility, but we always get to choose the maximum. And then we're going to finally add up the value for this is going to be the sum of those three things. So if we sum this out, we end up with a factor on forecast, we end up with a factor on forecast, which is the maximum of all those three values. That's what we're eliminating it by maximization. But we also end up with this decision function that says, what should we do? So that's when we eliminated D by maximizing. And here, it says returns an optimal decision function, which is and a new factor. So this is the optimal decision function. And this is the optimal decision function, and this is the new factor. We're going to maximize. And we can maximize this only when we know the forecast, because we're going to know we're going to observe the forecast before we act. So we can actually implement this. We can't implement, if I reset the query, weather umbrella, this one. I can't maximize at this stage because I can't decide to take it if it's going to be, leave it at home if it's going to be sunshine, because I don't know if it's sunshine. Right? So I can't maximize at this stage because I don't know. I can't implement this. Right? I can say if it's sunshine, I should leave it at home, and if it's rain, I'll take it, but I don't know I can't implement that because I don't know whether it's going to be sunshine or rain. I only see the forecast. Okay? Any other questions? Yeah.
So just to clarify, when we maximize by, we're basically setting an outline for like if test is this way, the result is this way, and then by an outcome by.
Yeah, so this ends up with, let's go back here. So this is sort of like a program. Weather forecast. Hang on, let's sum out weather. Right, this is the program that says if it's rainy, take it, else leave it at home. So it's if rainy, take it. If the forecast is rainy, take it, else leave it at home. That's my function, is a function of the parents. It says what I'm going to do. Okay, any other questions? All right. Let's get back to here. I've lost. Right, so we're going to eliminate by first. We're going to eliminate the last one first. All right. Let's keep going. Let's do the whole algorithm. It might be fun. After eliminating by, which we're going to do by maximization, a factor on which variables remain? So remember, I had this factor on result, test, and by, which is this one. And now I'm going to maximize over by. All right, how are we going here? Do we need more time? Anyone need more time? 3, 2, 1, we're about right. Yay. Test and result. Right, it's this factor. We're going to maximize over this. We're going to have a factor on test and results. We're going to maximize over by. We're going to choose the best by for each combination of test and result. Okay, so we're just going to maximize this. We have some factor. Then we're going to max, let's call this F1. So we're going to do max. We're going to do the maximum over by of F1 of result, test, and by. Is some factor F2 of just test and result. Okay, next one. Next question. What is eliminated next after eliminating by? So we've eliminated by. We've got this stage here. Now the question is, what are we going to eliminate next? Are we going to sum out result? Are we going to maximize test? Either one, it doesn't matter, or there's nothing more to eliminate. There's my algorithm. All right, how are we going? Does anyone need more time? All right, 3, 2, 1, we'll stop. Oh. All right. The answer is A. We can't maximize tests. We can't say if the car is good, do this test. If the car is bad, do a different test. Right? We can't maximize tests because that would rely on us saying, you know, if the result is good, if the result is passed, test for the engine, else test transmission or something. Right? We can't do this. The laws of physics and common sense and everything else tell us we can't do this, right? We can't decide on the test depending on whether we pass it or not. Because otherwise, if you're going to get a really good health check, then what you want to do is to get the worst test for something really bad. And if you knew what result you were getting. But what you can do is instead to sum out the result. And then we get just a function on test. So the answer here is A. Any questions about that? So play with these, doing an assignment. I want you to just play with it and work out what's going on because it's not that complicated, really. Okay, any other questions about this? We're going to maximize this. All right. So we're going to end up with a policy. So what does the policy specify? Does it specify just a value for test, just a value for buy, a value for test and a value for buy, or a value for test and a result for buy for each value of test and result, or just a value for buy for each value of test and result? So what does the policy end up being? All right, anyone need more time? We're getting there. Okay, 3, 2, 1, we'll stop. Oh, that's exciting. The answer here is D. It's going to specify both whether we should test and a function of buy from test and results. It's going to tell you a value for test and a value for buy for each value of test and result. Right? C is not right. We just can't, we're not going to say test the initial and buy is true. We're not going to say, we're actually going to say buy if the result is good. Right? And don't buy if the result is bad is the sort of thing we're going to do in here. We're not going to tell you whether to buy or not. We're going to tell you buy conditionally on the result. The whole purpose of doing this result here is to work out whether to buy. The whole purpose of the result is it's going to change whether we buy or not. So effectively here we're generating a small little program that tells us what we're going to do in the future. Okay, and it's going to specify both whether to test and whether to buy as a function of the result. Okay, any questions about that? All right, good. Good. All right, that was fun. That's how we learn things, by playing and doing and testing what we know. Okay, all right. All right, so what we're going to do today is we're going to talk about something called the value of information and the value for control. Actually, this week we're not really going to do anything new. We're going to play with some weird applications and interesting applications of the things we've already learned. We're going to do a little bit about where the probabilities come from. And then we're going to, actually we won't get to the stage of Markov chains. Okay. So first of all, let's look at the complexity of this algorithm. And so we have a decision D has k binary parents. Right, so we have a decision node, D, and it has parents V1, up to vk. And the question is, how many assignments of values to the parents are there? And each of these are binary. How many assignments of values to the parents are there? Sorry, 4? Someone else said, why would there be 4? So they're k parents. And they're each binary. They each have 2 different values. How many are there? Someone said it. A few people said it, but I've forgotten it. How many assignments of values to the parents are there? Right, there are 2 to the k assignments of values to the parents. We could build a big table of v1 to vk, right? And this has had 2 values, say 0 and 1. This could be 0, 0, 0, 0, and then 0, 0, 1, and then all the way down to 0, 1, 0, and 0, 1, 1, and 1, 0, 0, 0, right? All the way down to 1, 1, 1, 1, 1, 1, 1. Right, there's all these 2 to the k different binary numbers with k things. Any questions about that? Okay. How many different decision functions are there? What do we have to do for decision function? Remember what a decision function is. We have to specify a value for this. We've got to fill in this table, right? We've got to fill in this user interface. We've got to give a value for this parent. We've got a value for this parent and a value for this parent, all the way down to here. So how many of those are there? How many different decision functions are there? How many ways are there to fill in this? B. Right, this is B here. And how many ways to fill in this? B, right? So how many ways are there to fill in, if you had just to fill in those 2, how many ways are there? How many ways are there to fill in this B, 2 of them? Right, B squared ways. So how many in total? What is it? So b to the k, someone said. Is that right? How many parents are there? How many so for each assignment of the parents, you've got to do this. How many assignments of the values to the parents are there? Yeah. Right, b to the 2 to the k. And this grows really quickly. If you think exponential growth is bad, you should see this. This is horrendous. You soon get up to mass the number of elements in the universe and all sorts of things very quickly. So there are b to the 2 to the k decision functions. And if there are multiple decision functions, the number of policies is the product of the number of decision functions. However, there's this many decision functions. So if you thought about enumerating all of these decision functions, enumerating all these little, effectively, programs, you'd never get anywhere. But we do much better than that. Right? So this many decision functions. How many optimizations do we do in our algorithm? How complex is our algorithm? Our variable elimination algorithm? I this variable elimination algorithm we've been doing, how many optimizations is it? Well, don't we maximize for this one? We maximize for this one. We put in the value here. We maximize for this one. We put in the value here. We maximize for this one. And we maximize for this one. Right? So we do them each separately. And so how many does that give us? How many does that give us? That gives us just one for each value assignment to the parents. So we only do 2 to the k maximizations. So this algorithm is exponentially faster than sort of enumerating all of the policies and trying to evaluate them all. We end up with a much less complex algorithm than you would if you tried to maximize all these values. So it's the sum of this number of assignments, the values to the parents, which is just 2 to the k. So we're exponentially more efficient than searching through the space of decision functions. You might think, let's search through this space like we did when we were doing when we're trying to optimize these things. This dynamic programming algorithms, of which variable elimination here is exponentially faster than that. The search space is so much smaller than doing this. All right, any questions about that? All right. All right, let's get on to something simpler but almost deeper. So I want to know the question here. I want to know in here what happens if we add an arc from weather to umbrella. Let's go here. Let's move this to here. Let's optimize this. Oh, can I toggle monitoring? All right. I did do this. I've optimized it. What happens if I added an arc from weather into umbrella? What does that mean? What do the arcs into the decision node mean? What will happen? So initially it's 77. So the, right, so here means when we decide the umbrella, we're going to know the weather and the forecast when we take the umbrella. Right, so it means that we're going to know the weather, the future weather here, when we take the umbrella. So this one here, so this node here has value 77. So this network here, whoops, had value 77. When I optimized it. Now let's go to here. All right, what's going to happen to the value 77 when I add the arc, when I optimize the decisions? Yeah, it's going to should increase, but can't go down because every option that was available to us before was available to us then. So let's do this. Create an arc. All right, now we can go and solve it. Now we can optimize the decisions. And notice you have an interesting thing here. It's interesting now what's going to happen here is this wording here was sort of peculiar and sort of unnatural if it's only in a factor with some of its parents. And this is the reason we're going to do this. So now what are we going to sum out? What are we going to sum out here? What are we going to sum out first? There's only two choices, weather or forecast. Are they both parents of umbrella? Yes, I can't sum either of those two out. So I'm just going to maximize. But if I look at when I maximize this, I'm going to find weather umbrella, whoops, this one. I'm going to find that umbrella isn't in a factor with all of its parents. It's in a factor with just one of its parents. And in fact, it turns out that forecast is just irrelevant to us. We don't care what the forecast is because we get to observe the weather. So here we can just maximize it, and we can maximize it if we're just going to leave it at home. We're going to leave it at home if it's sunshine, and we're going to take it if it's rainy. So we're going to either get 100 or 70 depending on the weather. So the forecast is irrelevant. And that's why in here we had this funny wording of with a subset with some of its parents. It's in a factor with some of its parents. The only factor that it's in has just some of its parents, because here we don't have all of its parents in a factor. And if we do this, we can maximize umbrella. Then we can marginalize out forecast and weather, and we end up with 91. Right, so we're going to end up with with 91 when we add that in. So we're going to increase this value here. Okay, any questions about that? Yes? Forecast is irrelevant here because we can maximize the weather independently of, because it's actually separated from the utility given the other parents. So if you wanted to do it in terms of separation and independence, then but the other way of thinking about it is just when you're maximizing umbrella, we don't care about. We just have some smaller factors, the easiest way to think about it. We don't need all of the information. We can ignore information that's irrelevant. And we know here, just by going backwards, that we end up a factor with just umbrella and weather, so the forecast is irrelevant. All right. So now we're going to look at this value of information. So the value of information, knowing X at decision D, is the utility of the network with an arc from X to D, plus any no forgetting arcs, because we're not allowed to forget things, minus the utility of the network without the arc. So in here we go from 77 to 91, so the value of this information here is whatever the difference is. What is it? 14 or something. Okay, so the value of information here is 14. Right. If I knew the weather, then what's the value of the forecast? So if I have this network, what's the value of the information of weather given forecast is 14. What is the value of this network? Oops, that's a square note. So what I've done here is I've removed this arc. What's the value of this network? Which is what? Same as what? What's the value of this node, the utility for this network? What's the expected utility of this? 91, right? So the value of the information of the forecast, given the weather, is 0. So the value of the information of the forecast, of the forecast, given we know the weather, is 0. Right? If we're given the weather, the forecast is not any use to us. It's not valuable information. But if you look at the difference between this network. Well, is this going to be worse or less than these other ones? Right, so this one here is going to be worse. So if I remove these two things, I sort of have no information. I have to make a decision blind. Or I have to decide whether to take the umbrella before I've observed anything. So let's do that quickly because we're running out of time. Let's create a mode. Oh, let's delete this arc and delete this arc. And we're going to solve it. And I'll just do it briefly, and we'll find out that it's 70. Right, this one's actually 70. And the value of the information of the forecast, if we didn't know anything, is 7. So the forecast is worth 7 to us. Right, so if you start with this one, and you get 7. Right, so it's all talking about how much if we get more information. All right, let's. Okay. All right. The value of information is always non-negative. By adding arcs, it just never goes down because every possibility that was available to us before is still available to us. This node here can't be less than it because any policy I can implement here, I can implement here. So if I had a really good policy here, I can still implement it here, but I have more options to implement different policies. Interestingly, it's positive if and only if the agent changes its action. The only way we're going to get more value is if you actually change your action depending on it. Right, so the fact the policy here is going, when I go from here to here, I'm going to change my policy by conditioned on the weather here. Going from here to here, I didn't change my policy. I had the same policy no matter what the weather was, so it's not going to increase. And it's going to tell us how much information, we're going to talk about how much information, we can think about how much a sensor is worth. Right, how much would a bet, so we can think here, we have this forecast, how much would a better sensor of the weather cost? Well, the maximum it can be is 14. Because even if we knew perfect information, the maximum this sensor would be worth is 14 to us. Okay, so we can work out the value of better sensors. This particular sensor was worth 7. Finding out the forecast to us is worth 7. It's possible if you improve your forecast, it's possible to get up to 14, but it's not possible to get better than that. We can't build the better sensors. Better sensors aren't worth anything to us. And the only thing we have to be worried about adding an arc to cycles, yeah. These two? No. Well, they're just different. This says this one, that sense is better than this one. It's better to know.
But then can you draw an kind of value of information?
Right.
Because they don't contain.
Right, so value of information is sort of a myopic. Add one thing to something else. So this one here, to get from here to here, you have to subtract 1 and add 1. But we're just talking about the value of just having one piece of information. And pieces of information depend on other pieces of information. Right, so it depends on what other information you have. But just play with it. The assignment I want it to be play and tell me what you find. So play with, when you're doing it, try and add more arcs, see what happens, play, and all right, let's stop there. Oh, I have assignments here. Assignment